Tonight, as the world grows quiet and the sky stretches endlessly above you, we are going to the very edge of understanding, into a place where space folds inward, where time slows almost to a whisper, and where the laws of physics themselves begin to tremble. At the heart of every black hole, hidden behind the event horizon where not even light traveling at 299,792 kilometers per second can escape, lies something called a singularity, a point of zero volume and infinite density. It is where Einstein's equations break down, where gravity becomes so extreme that space-time curves without limit, and where our knowledge reaches its boundary. Most people scroll past mysteries like this, but not you. You're here because something about the universe ending, and possibly beginning again, pulls at you. What if singularities are not just endings but gateways? What if the entire observable universe, spanning 93 billion light-years across, once existed compressed into something smaller than an atom? Welcome to Velorin's Sleepy Space Mysteries, where we explore the deepest cosmic questions slowly, gently, and with wonder. In this journey, we will move through black holes, Hawking radiation, the information paradox, and the quiet future of a universe heading toward heat-death trillions upon trillions of years from now. If you don't want to miss where this story leads, subscribe, like this video, turn on the notification bell, and consider joining our membership to travel even deeper with us. And before we drift further, tell me in the comments where you're listening from tonight. Let's see how far across Earth this signal of curiosity has reached. Imagine a star at least 20 times more massive than our Sun reaching the end of its life. For millions of years, it has lived in a delicate balance. Deep in its core, nuclear fusion has been converting hydrogen into heavier elements, releasing energy that pushes outward with immense pressure. At the same time, gravity has been pulling everything inward, trying to compress the star under its own weight. As long as fusion continues, these two forces remain in equilibrium, like a perfectly tuned scale. But fusion is not eternal. When the core runs out of fuel, the outward radiation pressure weakens. Gravity, patient and relentless, does not weaken. It waits. And when that balance breaks, gravity wins. The collapse begins in less than a second. The core, no longer supported by fusion, implodes at a significant fraction of the speed of light. Temperatures soar into the billions of degrees. In that brief moment, the star's outer layers may explode outward in a supernova, shining brighter than an entire galaxy. But what remains at the center depends on mass. If the leftover core is less than about 3 times the mass of our Sun, neutron degeneracy pressure, a quantum mechanical effect arising from the Pauli exclusion principle, can halt the collapse, forming a neutron star. But if the remaining mass exceeds roughly 3 solar masses, even that quantum resistance cannot stop gravity. There is no known force left to oppose it. The collapse continues inward without pause. A black hole forms. Around this newborn black hole lies a surface we cannot see directly, but whose existence is predicted precisely by Einstein's theory of general relativity. This surface is called the event horizon. It is not a wall. It is not made of matter. It is a boundary in spacetime itself. Once anything crosses it, There is no path that leads back out. Not even light, which travels at nearly 300,000 kilometers per second, can escape. The escape velocity at that boundary exceeds the speed of light, and since nothing can move faster than light, nothing returns. To a distant observer watching from safely far away, something extraordinary happens near this boundary. An object falling toward the event horizon appears to slow down. This clock seems to tick more and more slowly. This is gravitational time dilation, a direct consequence of spacetime curvature. The stronger the gravity, the slower time passes relative to distant observers. As the object approaches the horizon, its light becomes increasingly redshifted, stretched to longer and longer wavelengths. Eventually, it fades from view, not because it has vanished instantly, but because its signals become so stretched and faint that they blend into darkness. From far away, it appears frozen in time, hovering forever at the edge. This is not speculation or poetic metaphor. General Relativity, published in 1915, predicts these effects mathematically with stunning precision. Over the past century, those predictions have been confirmed again and again. We have observed gravitational lensing, where massive objects bend the path of light from distant stars, warping their images into arcs and rings. We have measured time dilation in strong gravitational fields. And in 2019, the Event Horizon Telescope collaboration revealed the first image of a black hole's shadow, a glowing ring surrounding a dark central region in the galaxy Messier 87. That image was not an artist's impression. It was a measurement of space-time bending around an invisible abyss. Inside the event horizon, if you could somehow follow the path of falling matter, gravity grows ever more extreme. The difference in gravitational pull between your head and your feet would increase dramatically. This difference is called a tidal force. On Earth, tidal forces from the moon gently stretch our oceans, creating tides. Near a black hole, tidal forces become catastrophic. They stretch objects along the direction of fall and compress them sideways. Physicists call this process spaghettification. It is not a whimsical name. It describes the literal stretching of matter into long, thin strands under extreme curvature of spacetime. And yet, even this violent stretching is not the final mystery. As one approaches the center, the mathematics of general relativity predicts something even stranger. The curvature of spacetime increases without bound. Density rises toward infinity. The equations describe a point of zero volume and infinite density, a singularity. In these equations, quantities do not merely become large. They diverge completely. Infinite curvature, infinite density, no size at all. But in physics, infinity is often a warning sign. When an equation yields infinity, it may not be telling us that reality itself becomes infinite. It may be telling us that our theory has reached its limit. Just as Newton's laws fail at relativistic speeds, perhaps general relativity fails at these extreme conditions. The singularity might not be a physical point of infinite density. It might be a signal that another layer of understanding is required. So as you let this image settle in your mind, imagine gravity not as a force pulling objects like invisible strings, but as geometry shaping the paths that matter and light must follow. In Einstein's description, mass and energy tell spacetime how to curve, and curved spacetime tells matter how to move. There is no tugging in the traditional sense. There is only shape. The black hole is not reaching out. It is bending the very fabric through which all motion occurs. And somewhere at the end of that bending, at the place where our equations falter, lies a mystery. Not a monster, not a void of terror, but a boundary of knowledge. A place where one of our greatest theories stands magnificent and yet incomplete. A reminder that even the most successful descriptions of the universe are part of a larger story still unfolding. If you are still listening, gently type 1 in the comments. Now let us move closer, not physically, but conceptually, to that boundary where gravity bends reality so completely that even our language begins to strain. When we speak about gravity in everyday life, we describe it as a force. It pulls apples from trees, keeps the moon in orbit, holds us gently against the surface of Earth. But in the framework of general relativity, gravity is not truly a force at all. It is curvature. Imagine spacetime as a vast, flexible fabric. Place a massive object upon it, and the fabric dips. Smaller objects follow the curves created by that dip. They are not being pulled in the ordinary sense. They are following the straightest possible paths through a curved landscape. Near a black hole, that landscape becomes so steep that all possible paths lead inward. If you could hover just outside the event horizon, safely distant from the tidal forces, you would witness light behaving in ways that feel almost dreamlike. Photons passing near the black hole would not travel in straight lines. Their paths would curve around the object, sometimes looping entirely before escaping. This bending of light, gravitational lensing, is one of the clearest demonstrations that spacetime itself is curved. In some cases, light from stars behind a black hole can circle it multiple times, creating rings and arcs that astronomers can detect. The universe becomes a hall of mirrors shaped by gravity. As you imagine this, consider the strange experience of time in such a region. Clocks deeper in a gravitational well tick more slowly than those farther away. This is not illusion. It is measurable. If one clock sits near a black hole and another remains far from it, the one near the black hole will record less elapsed time. Time itself stretches. The closer you approach the event horizon, the more extreme this stretching becomes. From the viewpoint of a distant observer, the infalling clock appears to slow to a crawl. Seconds become minutes, minutes become hours, and eventually the ticking fades into near stillness. Yet for the traveler falling inward, nothing feels unusual about their own clock. Their heartbeat remains steady. Their thoughts proceed normally. The distortion is not experienced locally. It is a difference between perspectives woven into the geometry of spacetime. This duality reveals something profound. Reality near a black hole depends on where you stand. From far away, the horizon seems like a frozen boundary. From up close, it may feel like just another region of space passed without ceremony. General relativity allows both descriptions simultaneously. They are not contradictions. They are consequences of curved spacetime and the relativity of simultaneity. The universe is not absolute in the way it once seemed. It is relational, shaped by mass and motion. As matter continues its inward journey beyond the event horizon, all possible futures point toward the center. In ordinary space, you can choose to move left or right, forward or backward. Inside the horizon, the geometry changes so drastically that moving inward is no longer a choice. It is as inevitable as moving forward in time. In fact, some physicists describe the singularity not as a place in space but as a moment in the future. Just as tomorrow lies ahead of you in time, the singularity lies ahead of you in spacetime once you cross the horizon. There is no path that avoids it because all paths curve toward it. And yet, when we follow the equations all the way to that central point, we encounter infinities again. Infinite curvature, infinite density. These infinities suggest that spacetime, as described by general relativity, becomes infinitely warped. But physics rarely tolerates true infinities. They are signals that something is missing. At extremely small scales, quantum mechanics governs reality. It describes particles not as solid points, but as probability waves. It introduces uncertainty, fluctuations, and discrete quanta of energy. General relativity, on the other hand, treats spacetime as smooth and continuous. When the smooth fabric of relativity meets the jittering granularity of quantum theory under extreme gravity, we do not yet have a complete description. Some researchers suspect that at the heart of a black hole, spacetime may not collapse into an infinitely dense point at all. Instead, quantum effects could create a new structure, perhaps a tiny but finite region where gravity is balanced by quantum pressure. Others speculate that singularities might connect to other regions of spacetime, forming bridges or tunnels sometimes called wormholes. These ideas remain speculative, but they arise from the recognition that infinity in our equations is a boundary, not necessarily a destination. As you breathe slowly and let these ideas settle, imagine gravity as architecture rather than aggression. The black hole is not devouring in anger. It is shaping a region where geometry becomes extreme. Light curves because the stage on which it travels is curved. Time stretches because the rhythm of spacetime itself changes under immense mass. The universe is not tugging at objects like a fisherman pulling a line. It is sculpting pathways through which everything must move. In that sculpture lies a quiet lesson. The laws of physics that describe planets and stars with elegance begin to falter at the edge of a singularity. Not because they are wrong, but because they are incomplete. Somewhere between the immense curvature predicted by general relativity and the flickering uncertainty described by quantum mechanics, there may exist a deeper theory, one that unites them into a single coherent framework. Physicists call this hoped-for synthesis quantum gravity. We do not yet possess it, but the black hole stands as a signpost pointing toward it. So as you rest in this thought, see the black hole not only as an endpoint, but as an invitation. An invitation to question, to refine, to look beyond the boundaries of our current understanding. Gravity bends reality in ways both measurable and mysterious. And at the deepest bend, where curvature becomes extreme and time nearly whispers to a halt, the universe is quietly telling us that there is more to learn. Let us continue inward, not in fear, but in curiosity, toward the region where tidal forces begin to dominate experience. Imagine falling freely toward a black hole, far enough from the event horizon that the gravitational pull feels gentle and uniform across your body. In free fall, you would feel weightless, much like an astronaut orbiting Earth. Gravity would not feel like a crushing force. Instead, you and everything around you would accelerate together along the curved geometry of spacetime. This is one of the subtle beauties of general relativity. Gravity does not press on you in free fall. It guides you, but as you draw closer to the center, the difference in gravitational pull between your head and your feet grows stronger. This difference is the tidal force, and near a stellar mass black hole it becomes extreme very quickly. If your feet are slightly closer to the center than your head, they experience a stronger gravitational acceleration. The lower part of your body is pulled more strongly than the upper part. At the same time, gravity squeezes you from the sides, compressing inward. The result is stretching in one direction and compression in the perpendicular directions. This elongation intensifies dramatically as you descend. The term spaghettification may sound playful, but it captures the physical process accurately. Matter is drawn into a long, thin configuration by differential gravitational forces. The closer the singularity, the more dramatic the effect. For smaller black holes, this stretching would become lethal well before you reached the event horizon. For supermassive black holes, the horizon is larger and tidal forces at the boundary can be mild, allowing you to cross without immediate disruption, though deeper inside the stretching would eventually become unavoidable. As you imagine this descent, remember that nothing unusual marks the crossing of the event horizon itself, at least according to classical general relativity. There is no flash, no solid surface. The horizon is a boundary defined by the paths that light can or cannot take. Once crossed, every possible future direction leads further inward. You cannot fire rockets strongly enough to escape, not because the black hole actively restrains you, but because spacetime has curved so completely that outward paths no longer connect to the external universe. It is as if all roads tilt downhill toward a single destination. The mathematics describing this interior region is elegant and unforgiving. Solutions to Einstein's field equations show spacetime curvature increasing as radius decreases. The equations predict that as you approach zero radius, curvature tends toward infinity. In simplified terms, density equals mass divided by volume. As volume shrinks toward zero while mass remains finite, density grows without limit. Curvature, which depends on how spacetime bends in response to mass and energy, also diverges. But again, infinity here may not describe a literal physical state. It is the signal of a breakdown in description. Whenever our equations produce infinities, physicists grow cautious. Such results often mean we are applying a theory beyond its valid domain. Consider how classical physics once predicted that an electron orbiting a nucleus should radiate energy continuously and spiral inward, collapsing atoms entirely. That prediction implied instability and contradiction. The resolution came not by forcing the old equations to behave, but by developing quantum mechanics, which revealed that electrons occupy discrete energy levels. The infinity was not reality. It was a signpost. Similarly, the singularity predicted inside black holes may indicate that general relativity, though immensely successful, cannot be the final word. At extremely small scales, spacetime may not be smooth. It may possess a quantum structure, a kind of granular texture that prevents true infinite collapse. Some theoretical approaches attempt to reconcile these extremes. Loop quantum gravity suggests that spacetime itself could be quantized, composed of tiny discrete units that resist infinite compression. In certain models, collapse might halt at a very small but finite scale, replacing the singularity with a highly dense core. String theory proposes that fundamental entities are not point particles but tiny vibrating strings whose extended nature could soften the infinities predicted by point-like descriptions. There are even speculative scenarios in which the interior of a black hole transitions into a new expanding region of spacetime, though such ideas remain unproven. What unites all these efforts is the recognition that the singularity is less a final answer than a question written in mathematics. As you let your breathing remain slow and steady, shift your perspective again. Imagine gravity not as something aggressive, but as curvature intensifying. The stretching of matter, the redshifting of light, the slowing of clocks, all arise because spacetime is no longer gently curved as it is near Earth. It becomes steep beyond intuition, and yet the equations governing that curvature are precise. They have predicted the precession of Mercury's orbit, the bending of starlight near the Sun, the existence of gravitational waves rippling across billions of light years. When two black holes merge, they send waves through spacetime itself, oscillations measured by detectors on Earth. Those ripples are confirmations that spacetime is dynamic and responsive. Inside a black hole, that responsiveness becomes extreme. The geometry funnels all trajectories inward. From the outside, the object appears frozen at the horizon. From the inside, descent continues inexorably. These dual descriptions coexist without contradiction. Reality accommodates both viewpoints because spacetime is relative to observers. There is no single universal clock dictating events everywhere. Each observer carries their own measure of time shaped by gravity and motion. And so we arrive again at the threshold of the singularity, where curvature tends toward infinity in our equations. Rather than picturing a destructive point, picture instead a boundary of knowledge. The black hole interior is not merely a graveyard of matter. It is a laboratory at the edge of theory. It is where gravity and quantum mechanics must ultimately reconcile. Somewhere between the smooth continuum of relativity and the probabilistic discreteness of quantum physics lies a deeper structure of reality. The singularity is the place where we are reminded that our understanding, however powerful, is not yet complete. Let that thought rest gently. Gravity bends reality not to end it, but to reveal the limits of our insight. And at those limits, curiosity continues to move inward, searching for a theory capable of describing what lies beyond the infinities. Now let us pause at the edge of that predicted singularity and look at it with calm curiosity rather than alarm. When the equations of general relativity tell us that density becomes infinite and curvature becomes infinite, they are describing a mathematical limit. But nature rarely presents us with literal infinities. In most areas of physics, infinity marks the boundary where an approximation fails. It is the sign that two frameworks are colliding. At the center of a black hole, gravity becomes so strong that the smooth description of spacetime given by relativity must eventually meet the grainy, fluctuating world of quantum mechanics. And at that meeting point, our current theories do not yet fully agree. General relativity treats spacetime as a continuous fabric. It can stretch, bend, ripple, and curve without any smallest unit. Quantum mechanics, by contrast, tells us that energy and matter come in discrete packets. Even empty space is not truly empty. It is alive with fluctuations, tiny quantum events that appear and disappear in fleeting instants. When gravity is weak, these two pictures coexist without obvious conflict. But inside a black hole, where curvature grows enormous and distances shrink toward unimaginable scales, the two descriptions must overlap. We expect that spacetime itself may have a quantum structure, perhaps composed of indivisible units far smaller than atoms, far smaller even than protons. If such a quantum structure exists, it could prevent true infinite collapse. Instead of compressing into a point of zero size, matter might reach a state of extreme but finite density. Some theoretical models suggest that the collapse could rebound at microscopic scales, replacing the singularity with a region where gravity and quantum pressure balance each other. Others imagine that spacetime might twist in such a way that the interior connects to another region entirely, though such possibilities remain speculative. What matters is not the specific proposal, but the shared recognition that infinity in our equations likely signals missing physics. As you imagine this, notice how the black hole transforms from a symbol of destruction into a boundary of discovery. It is not merely the endpoint of a massive star. It is a doorway to deeper understanding. The equations that describe its formation are among the most precise in science. They predict the size of the event horizon, the shape of spacetime around it, and the way light bends in its vicinity. Observations confirm these predictions with astonishing accuracy. And yet, at the very center, those same equations dissolve into infinities. This is not failure. It is an invitation. Consider again the balance that once sustained the massive star. Outward radiation pressure matched inward gravitational pull. When fusion ceased, gravity dominated. But gravity does not simply crush without order. It reshapes geometry. It reorganizes spacetime so thoroughly that what we interpret as force is actually curvature. If you were falling inward, you would not feel a tug dragging you toward the center. You would feel weightless, following the straightest possible path in a curved landscape. Only the growing tidal differences across your body would signal how extreme that landscape has become. And as spacetime curves more sharply, time itself continues to stretch. From far away, an infalling object appears to slow and fade. From its own perspective, it continues smoothly forward. This duality teaches us something subtle about reality. There is no single, universal vantage point that captures the whole story. Physics allows multiple perspectives, each internally consistent. Near a black hole, these perspectives diverge dramatically, yet both remain valid within their frames. The singularity, then, may not be a physical object waiting at the center. It may be the limit of a coordinate description. In some formulations of relativity, singularities arise because certain coordinate systems break down under extreme curvature. Change the mathematical lens and the picture can shift. This does not eliminate the underlying mystery, but it reminds us that what appears absolute in one description may be more nuanced in another. As you breathe slowly and let your thoughts settle, imagine gravity as architecture once more. The black hole is not a cosmic vacuum cleaner indiscriminately devouring matter. It is a region where geometry narrows, where every possible path bends inward. Light circles and spirals. Clocks tick at different rates. Matter stretches and compresses. All of it follows from one principle: mass and energy curve spacetime, and curved spacetime guides motion. And somewhere beyond the reach of our current equations lies the deeper structure that unites gravity with quantum uncertainty. Perhaps spacetime at its smallest scale is not smooth, but woven from tiny loops or vibrating strings or something even more fundamental. Perhaps the singularity is replaced by a finite core or a transition to another domain of reality. We do not yet know. What we do know is that black holes push our theories to their limits. They reveal the strength of general relativity and simultaneously expose its incompleteness. So instead of picturing an abyss of infinite destruction, picture a threshold. The star's collapse did not end in chaos. It led to one of the most precise and elegant predictions in physics, a region where geometry becomes extreme. And at the deepest point of that region, where our equations falter, the universe seems to whisper that there is more to uncover. Gravity bends reality not only by shaping the paths of matter and light, but by guiding our understanding toward its own edges. In that sense, the black hole is both a product of stellar death and a beacon for theoretical rebirth. It stands at the intersection of the vast and the minute, of curved spacetime and quantum fluctuation. And as you rest in this thought, allow yourself to feel the quiet wonder of it. The gravity that bends reality does not merely pull inward. It bends our curiosity forward, toward the deeper theory still waiting to be found. As we reach the final stretch of this descent into gravity's deepest expression, let us pause not at the singularity itself, but just before it, in the conceptual space where understanding begins to blur. Everything we have followed so far, the collapse of a massive star, the formation of the event horizon, the bending of light, the stretching of time, the tidal forces that elongate matter, all of it arises from one central idea: mass and energy curve spacetime. The greater the mass compressed into a region, the steeper that curvature becomes. A black hole is not a hole in the ordinary sense. It is a region where curvature grows so intense that every possible path through spacetime leads inward. It is geometry taken to its extreme conclusion. If we step back for a moment, we can see that black holes are not exotic exceptions to the rules of the universe. They are natural consequences of those rules. The same equations that describe the orbit of Earth around the Sun also predict black holes when mass becomes sufficiently concentrated. There is no special clause in the laws of physics that says, "Stop here." Instead, the mathematics flows smoothly from gentle curvature to extreme curvature. Planet curves spacetime slightly. A star curves it more strongly. A collapsing core curves it so steeply that a horizon forms. This continuity is what makes black holes so compelling. They are not violations of general relativity. They are its triumph. And yet, that triumph carries us directly to the edge of mystery. When curvature becomes infinite in our equations, we are forced to confront the fact that a smooth geometric description may not survive at arbitrarily small scales. Perhaps spacetime has an underlying quantum structure, subtle and discrete. Perhaps at distances comparable to the Planck length, about 1 part in 10 to the 35 meters, the familiar notion of a continuous fabric dissolves into something more fundamental. We do not yet know, but we do know that general relativity and quantum mechanics, our two most successful theories, describe different domains with astonishing accuracy. Relativity governs the cosmic vastness of galaxies and black holes. Quantum theory governs the microscopic dance of particles and fields. At a singularity, these domains overlap. That overlap is where a deeper theory must eventually emerge. Consider how strange this is. The same universe that allows atoms to exist in stable configurations also allows entire stars to collapse into regions from which light cannot escape. The same reality that permits quantum fluctuations in empty space also permits gravitational waves to ripple across billions of light years. There is no separation between the small and the large except in scale. Black holes reveal this unity. They are where the large compresses into the small. They are crossroads where cosmic structure meets quantum uncertainty. If singularities signal incomplete understanding, then they serve as invitations rather than dead ends. They tell us that our description of spacetime as a smooth continuum may be an approximation, valid almost everywhere but not at the deepest core of collapse. In that sense, the singularity is less a physical object and more a boundary in theory. It is where our current language falters. And whenever language falters in physics, discovery often follows. The ultraviolet catastrophe led to quantum theory. The orbit of Mercury's subtle anomaly led to relativity. The infinities of black hole interiors may one day lead to quantum gravity, a framework that unites curvature and probability into a single coherent vision. Now let your mind shift gently away from equations and back to imagery. Imagine spacetime as a vast landscape. In most regions, it rolls gently like hills. Near massive stars, it dips more noticeably. Near a black hole, it plunges into a steep valley from which no path climbs outward. But even that valley is part of the same terrain. It is not separate from the rest of the universe. It is an expression of the same underlying geometry. Gravity does not rage. It shapes. It sculpts. It defines the contours along which light and matter travel. And perhaps that is the quiet lesson of the gravity that bends reality. What appears destructive from one perspective is, from another, simply structure taken to its limit. The black hole is not tearing the universe apart in anger. It is revealing how profoundly geometry governs existence. Time slows because the path through spacetime is altered. Light redshifts because the fabric it crosses is stretched. Matter elongates because curvature varies from point to point. Each phenomenon is a natural consequence of shape. As you relax into this understanding, notice how different it feels from imagining gravity as a pulling force. In this view, nothing is being dragged against its will. Everything follows the contours laid out by mass and energy. The universe is not tugging. It is guiding. And the black hole, far from being merely a symbol of annihilation, becomes a symbol of depth. A depth in curvature, in theory, in mystery. Somewhere beyond the point where our equations diverge, beyond the infinities that mark our ignorance, there may lie a more complete story. Perhaps space-time foams and fluctuates at the smallest scales. Perhaps singularities resolve into finite structures governed by quantum laws. Perhaps gravity itself emerges from more fundamental principles still hidden from view. We do not yet know, but the path toward that knowledge bends through the heart of black holes. So as your breathing grows slower and the images soften, hold on to this thought gently. Gravity is geometry. The universe is not a collection of disconnected objects pulling at one another. It is a single fabric whose shape determines every motion. And at the deepest bend of that fabric, where light cannot escape and time nearly whispers to silence, we find not only an abyss, but a question. A question about how reality is woven, about how the vast and the tiny fit together, about what lies beyond the limits of our current understanding. Somewhere at the end of those curved pathways, at the center of that profound bending, lies a mystery we are only beginning to trace. Now we move to a quieter paradox. In the 1970s, Stephen Hawking proposed something that felt almost gentle compared to the violent image of collapsing stars and crushing gravity. He suggested that black holes are not entirely black. They are not perfect cosmic prisons. Instead, through subtle quantum effects near the event horizon, they emit what we now call Hawking radiation. To understand why this matters, imagine the edge of a black hole not as a sharp boundary, but as a restless place. In quantum physics, even empty space is never truly empty. It flickers. Pairs of particles and antiparticles briefly appear and vanish, borrowing energy from the vacuum and returning it almost instantly. Normally, these pairs annihilate each other so quickly that the universe barely notices. But near the event horizon, gravity interferes. If one particle falls inward while the other escapes, the balance is broken. The escaping particle becomes real. From far away, it appears as though the black hole has emitted something. Slowly, quietly, the black hole loses a tiny bit of energy. And because energy and mass are equivalent, described by the simple relationship energy equals mass times the speed of light squared, the black hole loses mass as well. This loss is unimaginably slow. The universe today is about 13.8 billion years old. That number alone feels enormous. But a typical stellar black hole, perhaps formed from a star 20 times the mass of our Sun, would take on the order of 10 to the 67 years to evaporate. 10 to the 67 means a 1 followed by 67 zeros. If you tried to count that high, saying one number per second, you would never finish. And supermassive black holes, the giants sitting at the centers of galaxies, endure far longer. Some could last around 10 to the 100 years, a 1 followed by 100 zeros. Numbers so large they stop feeling like quantities and start feeling like landscapes. Compared to that, all of human history is less than a blink. Even the lifetime of stars becomes brief. Yet Hawking's idea carried a hidden tension. The radiation he described appeared to be thermal. That means it looked random, like the glow from a warm object. It did not seem to contain any detailed record of what had fallen into the black hole. If a book, a planet, or even an entire star crossed the event horizon, the outgoing radiation did not appear to encode the fine details of its structure. And here is where the quiet paradox begins. Quantum mechanics, the most precisely tested theory we have, insists on something profound. Information cannot be destroyed. If you take a piece of paper and burn it, the words do not vanish from the laws of physics. They are scrambled into ash, smoke, and heat. In principle, if you could measure every particle with infinite precision, you could reconstruct the original message. This principle is known as unitarity. It means that the evolution of a quantum system is reversible in theory. The universe keeps track of its states. It may hide them in complexity, but it does not erase them. So what happens when information falls into a black hole? If the black hole eventually evaporates into what appears to be random radiation, where did the detailed description of everything it swallowed go? Did it dissolve into nothing? If so, quantum mechanics would be wrong at a fundamental level. This is the black hole information paradox. It is not loud. It does not involve explosions or collapsing stars. It is a quiet contradiction between two of our deepest theories, general relativity and quantum mechanics. One describes gravity and spacetime with extraordinary accuracy. The other governs particles and probabilities with unmatched precision. But when we place them together at the edge of a black hole, they disagree. As you listen and let your breathing settle, consider how strange this is. A black hole forms from collapse, radiates slowly across timescales beyond imagination, and may eventually vanish entirely. But the universe, according to quantum law, is not allowed to forget what fell inside. Every particle, every quantum state, every configuration must remain encoded somehow. It suggests something almost comforting. Even in the most extreme places, nothing is truly lost. The universe may rearrange, compress, scatter, and transform, but it does not erase. Information is more durable than stars, more persistent than galaxies, more stubborn than gravity itself. And so the question lingers gently in the dark. If black holes evaporate and information cannot disappear, then where is it hiding? We will move closer to that question next. The tension deepens when we look more carefully at what Hawking radiation seems to be. In its original form, it carries no obvious fingerprint of what created the black hole or what later fell inside it. It depends only on a few large-scale properties: mass, charge, and spin. In physics, this simplicity is sometimes described by saying that black holes have no hair, no detailed features, no visible memory. Two black holes with the same mass charge, and rotation appear identical from the outside, even if one formed from collapsing stars and the other from something far stranger. That simplicity is elegant, but it creates a problem. If every complex object that falls into a black hole is reduced to just 3 numbers, then all the fine details of its structure seem to vanish. Quantum mechanics does not allow that kind of erasure. The equations that govern particles evolve smoothly and predictably. They scramble information, but they never delete it. If you know the exact quantum state of a system at one moment, the laws of quantum physics allow you, at least in principle, to determine its past or future states. It is like a perfect accounting system, one that never loses track of even the smallest transaction. Now imagine throwing a detailed object into a black hole, perhaps a hard drive filled with data. From the outside, the black hole grows slightly heavier. Later, over incomprehensible spans of time, it radiates away its mass as Hawking radiation. If that radiation is truly random, if it carries no trace of the original structure, then the information that once described that hard drive is gone. Not hidden, not scrambled, gone. And that is not something quantum theory tolerates. This contradiction is subtle but profound. It does not show up in everyday life. It does not affect how stars shine or how planets orbit. It emerges only when gravity is pushed to its most extreme limits and quantum effects can no longer be ignored. The black hole becomes a testing ground, a place where our 2 most successful frameworks are forced to confront each other. Some physicists once believed that perhaps information really is lost, that black holes represent a fundamental exception to the rules. But over time, that view has become less popular. The consistency of quantum mechanics is too powerful, too well supported by experiment. Instead, many researchers now suspect that Hawking's original calculation was incomplete, not wrong, but missing a deeper layer. Perhaps the radiation is not perfectly random. Perhaps hidden within its subtle quantum correlations is a delicate encoding of everything that ever crossed the horizon. To picture this, imagine shredding a book into microscopic pieces and scattering them across a vast field. To a casual glance, the pieces look random. But if you could gather every fragment and analyze the precise pattern of fibers and ink, you might reconstruct the original text. The information was never destroyed. It was dispersed in a way that made it almost impossible to read. A black hole, in this view, is not an incinerator. It is a cosmic scrambler. Everything that falls inside is mixed, tangled, and transformed into a new form so complex that it appears featureless. The outgoing Hawking radiation would then carry that information away bit by bit, encoded in correlations too subtle for us to detect with current understanding. This idea preserves the principle that the universe never forgets, but it demands a far more intricate relationship between gravity and quantum theory than we currently possess. And that is where the deeper issue reveals itself. We do not yet have a complete theory of quantum gravity. General relativity describes spacetime as smooth and continuous, bending under the influence of mass and energy. Quantum mechanics describes reality as granular and probabilistic, governed by wave functions and uncertainty. At the scale of a black hole's event horizon, these 2 descriptions overlap. The smooth geometry of spacetime must somehow reconcile with the jittering fluctuations of the quantum vacuum. Without a unified framework, our predictions become incomplete. The infinities that appear in singularities are often interpreted as signals that the theory has reached the edge of its validity. They are not necessarily physical infinities, but mathematical warnings. In the same way, the information paradox may be telling us that our current understanding is missing a crucial piece. Not because we lack intelligence or creativity, but because the universe is deeper than the tools we currently use to describe it. As you continue listening, let that thought settle gently. The paradox is not a failure. It is an invitation. It suggests that beneath the apparent conflict between evaporation and memory, there is a hidden coherence waiting to be uncovered. If information truly refuses to disappear, then even a black hole, the darkest object we know, must participate in that rule. And if that is true, then somewhere within the faint whisper of Hawking radiation, or across the surface of the event horizon itself, the universe is keeping a record far more faithful than we once imagined. One of the most compelling attempts to resolve this paradox is the idea that information is not hidden deep inside the black hole at all, but encoded on its boundary. This is known as the holographic principle. The name sounds abstract, but the intuition behind it is surprisingly simple. A hologram is a two-dimensional surface that contains all the information needed to describe a three-dimensional image. In a similar way, some physicists propose that everything that falls into a black hole is not stored in its mysterious interior, but written onto the event horizon itself, like data on a cosmic screen. The event horizon then is not merely a point of no return. It becomes a kind of ledger. Every particle that crosses it slightly alters its surface. Every quantum state leaves an imprint. The area of the event horizon, not its volume, turns out to be proportional to the black hole's entropy, a measure of how much information it contains. This discovery was one of the earliest clues that black holes might obey deeper informational rules. The entropy does not scale with how much space the black hole occupies, but with the size of its surface. That is strange. In ordinary systems, information scales with volume. In black holes, it scales with area. This shift in perspective changes everything. If the maximum amount of information inside a region of space is determined by its boundary, then perhaps the universe itself works this way. Perhaps our familiar three-dimensional world is, at a fundamental level, described by information encoded on a distant two-dimensional surface. The black hole becomes not an exception to physics, but a clue about its true structure. In this framework, when matter falls toward the singularity, its information is not crushed into oblivion. Instead, it is absorbed into the event horizon's microscopic degrees of freedom. The horizon becomes a dynamic, vibrating membrane at the quantum level, adjusting itself to account for every new arrival. Hawking radiation, far from being purely random, would then carry away this encoded information gradually as the black hole evaporates. The radiation would look thermal on average, but hidden within its fine structure would be correlations that preserve the past. There are other approaches as well. Some researchers argue that the information is not stored only on the surface, but subtly entangled with the outgoing radiation from the very beginning. In quantum mechanics, entanglement means that two systems can share a connection so deep that measuring one immediately affects the description of the other, no matter how far apart they are. If Hawking radiation is entangled in a complex way with the internal states of the black hole, then as more radiation escapes, the information could gradually leak out, not as a readable message, but as a delicate web of correlations. Recent theoretical work has strengthened this possibility. Calculations using simplified models of quantum gravity suggest that information may indeed be preserved, and that black hole evaporation is ultimately consistent with quantum mechanics. In these models, the entropy of the radiation follows a curve that first increases and then decreases, implying that information is not permanently lost but eventually returns to the universe in encoded form. The details are mathematically intricate, but the conclusion is gentle and powerful. The universe keeps its records, yet none of this is fully settled. We still lack a complete and experimentally confirmed theory of quantum gravity. String theory offers one path, suggesting that the fundamental constituents of reality are tiny vibrating strings whose interactions naturally encode information on surfaces. Loop quantum gravity offers another, proposing that spacetime itself is composed of discrete chunks woven together at the smallest scales. Both approaches attempt to reconcile relativity and quantum mechanics, and both hint that singularities may not be true infinities but regions where spacetime transitions into a new quantum phase. The paradox remains not because it is unsolvable, but because it sits at the intersection of our deepest ideas. It is a reminder that the universe is not only vast in space and time, but deep in principle. When we say that information cannot be destroyed, we are making a profound claim about reality. We are saying that every interaction leaves a trace, that every quantum state evolves without forgetting its origin, even if that origin becomes impossibly scrambled. As you drift further into stillness, consider what that means on a cosmic scale. The light from distant stars carries information about nuclear reactions that happened millions or billions of years ago. The cosmic background radiation preserves a faint echo of the universe's earliest moments. Perhaps in the same way, the faint whisper of Hawking radiation carries echoes of everything that ever crossed the event horizon. The singularity, then, may not be an eraser. It may be a transformer. What appears as destruction at one level becomes transformation at another. Information is not smashed into nothing. It is folded, encoded, redistributed into patterns too subtle for us to read. The black hole does not forget. It reorganizes. And if that is true, then the universe itself may operate on a principle of deep conservation, not only of energy or momentum, but of story. Every particle interaction, every photon emitted, every configuration of matter leaves a mark woven into the structure of reality. We may not yet know how to trace those marks through the extreme curvature of spacetime, but their persistence suggests something quietly reassuring. Nothing truly vanishes. It only changes form. There is another way to approach this paradox, one that feels almost philosophical in its implications. Instead of asking where the information goes, some physicists ask whether our understanding of space itself is incomplete. perhaps information is not something that moves around inside space, but something from which space emerges. In this view, spacetime is not the fundamental stage on which physics unfolds. It is a consequence of deeper informational relationships. If that is true, then a black hole is not a place where information falls into a hole in space. It is a region where the structure of information reorganizes so radically that our usual description of space breaks down. Consider how radical that shift is. We normally think of particles existing inside space, moving through it like actors on a stage. But quantum theory already challenges this intuition. Particles can be entangled across enormous distances. Their properties are not fully defined until measured. The geometry of spacetime, described so elegantly by general relativity, may itself be built from networks of entanglement. Some researchers suggest that spacetime curvature is related to the pattern of quantum connections between underlying degrees of freedom. If those connections are altered, geometry changes. From this perspective, the event horizon of a black hole is not just a boundary in space. It is a boundary in the flow of information. What appears as a one-way membrane may be a region where the underlying informational fabric is stretched to its limit. The singularity predicted by classical equations, with its infinite density and zero volume, could be signaling that spacetime as a smooth continuum no longer applies there. Instead of a true point of infinite compression, there may be a quantum core, a region where geometry dissolves into more fundamental elements. If information is primary and spacetime secondary, then the paradox begins to look different. The question is no longer how information escapes from inside a classical black hole. The question becomes how the informational structure reorganizes as the black hole forms and evaporates. In such models, information never resides in a hidden interior in the first place. It is encoded in the global quantum state of the system, including the radiation that eventually escapes. What seems like loss is simply our inability to track the full, entangled description. There is something almost poetic in this idea. The black hole, once imagined as the ultimate destroyer, becomes instead a reshaper of structure. It takes inordered matter, compresses it beyond recognition, and releases energy in a way that looks random but may contain hidden patterns. The universe, then, is less like a machine that discards parts and more like a vast transformation engine. Every input reappears, though perhaps in a form too subtle for us to decode. It is important to remember that this paradox persists not because physics is failing, but because it is advancing. Each time we have encountered a deep inconsistency in the past, it has led to new frameworks. When classical physics could not explain the spectrum of hot objects, quantum mechanics was born. When Newton's gravity could not account for the precise orbit of Mercury, relativity emerged. Paradoxes are often doorways. They indicate that two successful descriptions overlap in a regime where neither is complete. The black hole information paradox may be precisely such a doorway. It is pointing toward a theory of quantum gravity that unifies spacetime geometry with quantum information. We do not yet have the final form of that theory. We see glimpses in holography, in string theory, in approaches that treat spacetime as emergent. But the full picture remains out of reach, like a horizon we can approach but not cross. As you continue listening, allow the scale of this to soften your thoughts. The evaporation of a black hole over 10 to the 67 or even 10 to the 100 years is so slow that it feels timeless. During that span, galaxies will fade, stars will burn out, and the cosmic landscape will transform completely. Yet through all of that change, the principle that information endures may remain intact. The universe evolves, but it does not forget. Imagine the faintest whisper of radiation escaping a black hole in a far distant future. Each particle carries energy. Each particle participates in a quantum web that connects back to the entire history of what formed that black hole. We may never reconstruct that history in practice. The correlations may be impossibly complex, but in principle they exist. The past is not erased. It is woven into the present in ways too intricate for us to perceive. And so the singularity itself may not be a wall where reality ends. It may be a place where our descriptions end, while reality continues in a deeper form. The infinities in our equations are not statements about nature, but signals that our language needs refinement. When we say density becomes infinite, we are really saying our current framework has reached its limit. Beyond that limit, something more subtle is happening. If you let this idea settle, it becomes strangely calming. Even in the most extreme regions of the cosmos, even where light cannot escape and time stretches towards stillness, the underlying order persists. Information is conserved. Patterns endure. Transformation replaces annihilation. The universe is not careless with its history. It carries it forward, encoded in structures we are only beginning to glimpse. In the end, the paradox invites humility. It reminds us that our theories are powerful but provisional. They describe vast domains with astonishing precision. Yet at the edge of a black hole they begin to whisper instead of speak. And in that whisper is a promise that a deeper harmony exists, one in which gravity and quantum mechanics agree, and in which nothing that ever was is truly lost. As we come to the quiet center of this paradox, it helps to step back and look at the scale of what we are describing. A black hole forms from collapse, perhaps from a star many times heavier than our sun. It lives for spans of time that dwarf the current age of the universe. It slowly evaporates through Hawking radiation across 10 to the 67 or even 10 to the 100 years. And throughout that immense arc of existence, it never violates the deep rule that information cannot be destroyed. If that rule holds, then the entire lifetime of a black hole is not a story of swallowing and erasing, but of absorbing and transforming. Think about how counterintuitive that is. When something falls past the event horizon, it appears to vanish forever. No signal returns. No message escapes. To an outside observer, it is as if the object has slipped beyond reality. And yet, according to quantum principles, the full description of that object must remain encoded somewhere in the total state of the universe. The event horizon hides it from view, but it does not grant permission for deletion. This realization reframes the singularity itself. We often describe it as a point of zero volume and infinite density, a place where space-time curvature becomes infinite and our equations break apart. But infinity in physics is usually not a literal prediction. It is a signpost. It tells us that the theory being used has reached its boundary of applicability. Just as classical physics breaks down at the atomic scale and required quantum mechanics to replace it, general relativity likely breaks down at the singularity and requires a quantum description of gravity. The true core of a black hole may not be an infinite point, but a region where space-time dissolves into a new phase governed by deeper laws. In that deeper description, information would not pile up at an infinitely dense point. It would be encoded in microscopic degrees of freedom that we do not yet fully understand. The horizon might shimmer with quantum states. The radiation might carry delicate correlations. The entire process of formation and evaporation might be one long, coherent evolution, never breaking the fundamental rule of reversibility at the quantum level. There is something almost reassuring in that continuity. The universe does not tear holes in its own logic. It may challenge our understanding, it may stretch our imagination, but it does not abandon coherence. The paradox exists because we are using two incomplete pictures at once. One sees gravity bending geometry into extremes. The other sees quantum states evolving with perfect fidelity. When we force them together without a unifying theory, tension appears. But tension in science is often a sign of approaching insight. As you drift deeper into calm, consider the broader implication. If information cannot be destroyed even by a black hole, then the universe possesses a kind of memory that extends beyond any single structure. Stars ignite and extinguish. Galaxies collide and disperse. Black holes form and eventually evaporate. Yet the informational content of these processes remains conserved within the grand quantum state of everything. The universe may change form, but it does not lose its history. Imagine every photon ever emitted by every star carrying a fragment of that history. Imagine every particle interaction contributing to an evolving tapestry that never erases its previous threads, only weaves them into new patterns. The singularity, once feared as the ultimate eraser, becomes instead a loom. It gathers strands of matter and energy, compresses them beyond recognition, and eventually releases them back into the wider fabric. Even the final evaporation of a black hole, in its last brief flash of radiation, would not be a destruction of story. It would be the closing movement of a transformation that began with stellar collapse billions or trillions of years earlier. What was once a star becomes a black hole. What was once a black hole becomes radiation dispersed across expanding space. And within that radiation, however scrambled, the imprint of the past remains encoded. The paradox remains unresolved in detail. We do not yet possess the full mathematics of quantum gravity. We cannot experimentally probe the interior of a black hole. We rely on theory, consistency, and indirect clues, but the direction is clear. Increasingly, evidence suggests that information survives, that evaporation and quantum law can coexist, that what appears random may conceal deep order. And perhaps that is the most calming thought of all. At the deepest edge of understanding, at the boundary where light cannot return and time stretches towards stillness, reality is not dissolving into chaos. It is reorganizing with fidelity to its own principles. The universe may be vast beyond comprehension, its timescales extending into numbers that feel abstract and unreachable, but its underlying logic is steady. If you are still here with the story, type 2 in the comments. Let us travel forward, far beyond the present age of 13.8 billion years, beyond the era when galaxies still sparkle and stars are born in luminous clouds of hydrogen. Our sun, like most stars of its kind, will shine for roughly 10 billion years in total. It will spend that time quietly fusing hydrogen into helium, balancing the inward pull of gravity with the outward push of radiation. More massive stars will burn brighter and die sooner, some lasting only millions of years before collapsing. Smaller red dwarfs, faint and patient, may endure for trillions of years, but even they cannot shine forever. As cosmic time stretches onward, star formation will begin to slow. The vast molecular clouds that once gave birth to new suns will thin. Hydrogen, the simplest and most abundant element in the early universe, will be gradually locked away inside stellar remnants. White dwarfs, neutron stars, and black holes. Without fresh gas to collapse under gravity, the universe will grow quieter. After roughly 100 trillion years, 10 to the power of 14, the last new stars may flicker into existence. Imagine that number for a moment, a 1 followed by 14 zeros. It is a span of time nearly 10,000 times longer than the universe has existed so far. By then, the bright spiral arms of galaxies will have faded. No new blue stars will ignite. Only the long-lived red dwarfs will persist, dim and steady, casting faint crimson light into increasingly empty space. Galaxies themselves will change. Over immense timescales, gravitational interactions will rearrange stars into more stable configurations. Many stars will be ejected into intergalactic space, becoming solitary wanderers in an ever-expanding cosmos. The expansion of space, driven by dark energy, will continue to push distant galaxies beyond our observable horizon. If an observer were alive in that far future, they would see only their local gravitationally bound group. Everything else would have slipped away, carried beyond the reach of light. Eventually, even the longest-lived red dwarfs will exhaust their nuclear fuel. They will cool into black dwarfs, stellar embers so faint they emit almost no visible light. The universe will enter what cosmologists sometimes call the degenerate era, a time dominated not by shining stars, but by remnants. White dwarfs slowly radiating away their heat, neutron stars cooling into darkness, planets orbiting dead suns, and at the centers of galaxies, black holes will remain. These objects, born from gravitational collapse, will become the dominant gravitational anchors of the cosmos. Supermassive black holes, millions or billions of times the mass of our sun, will sit in the darkened cores of merged galaxies. Smaller stellar mass black holes will drift silently through space. Over trillions upon trillions of years, gravitational encounters will cause many objects to spiral inward and be consumed. The universe will simplify. Fewer structures, larger gaps, longer silences, but black holes are not eternal. In the 1970s, Stephen Hawking showed that quantum effects allow black holes to emit radiation. This Hawking radiation is unimaginably faint for large black holes, but it is relentless. The power emitted is inversely proportional to the square of the black hole's mass. In simple terms, the larger the black hole, the colder and dimmer it is. A supermassive black hole might have a temperature far below that of the cosmic microwave background today. Yet, as the universe cools and expands, the background radiation will drop even further. Eventually, black holes will become warmer than their surroundings and begin, very slowly, to lose mass. The timescales are staggering. A black hole with the mass of our Sun would take on the order of 10 to the power of 67 years to evaporate completely. A supermassive black hole could endure for up to 10 to the power of 100 years. That is a 1 followed by 100 zeros. A number so vast it feels more like a horizon than a duration. And yet, even that is not forever. Over those immense epochs, black holes will shrink. As they lose mass, they grow hotter, radiating more intensely. In their final moments, after unimaginable patience, they will release a burst of energy and vanish. One by one, the last gravitational titans will fade into radiation. What remains then is a universe approaching what physicists call heat death. Not an explosion, not a collapse, but a gradual evening out. Energy will be evenly distributed. Entropy disorder will be maximized. There will be no significant gradients left to power stars, chemistry, or life. No pockets of concentrated energy to extract useful work from. Only thin radiation drifting across ever-expanding space. No structure, no light in any meaningful sense. Just a low, uniform glow stretched thinner and thinner as space continues to expand. If you imagine this far future, do not picture chaos. Picture stillness, a calm so complete that change itself has slowed almost to nothing. The universe, once filled with roaring fusion and gravitational drama, settles into equilibrium, a vast quiet beyond the last star. In that distant era, after the last star has burned out and the final black hole has dissolved in a brief whisper of radiation, the universe will not explode or collapse in any dramatic gesture. It will simply continue. Space will keep expanding. The distances between the remaining particles will grow wider and wider. Photons, stretched by expansion, will lengthen into wavelengths so vast that the very idea of light will lose its familiar meaning. What was once visible radiation will become something softer, thinner, more diffuse than any glow we know today. The cosmos will approach a condition of near-perfect thermodynamic equilibrium. Temperature differences will fade. Motion will slow. Entropy will reach its maximum, a state where no organized structure can arise because there are no gradients left to power transformation. This is what physicists mean by heat death. Not heat in the sense of fire, but heat in the sense of uniformity. A universe where everything is evenly spread, where no region is richer in energy than another, and therefore no work can be extracted. No engines can run. No stars can ignite. No chemistry can build complexity. only an almost featureless sea of low-energy radiation and sparse particles drifting in expanding emptiness. If an observer could exist then, which seems unlikely, they would see almost nothing. The sky would not be black in the way we imagine night. It would be something closer to blankness. Without stars, without galaxies, without even black holes to mark the dark with deeper shadows, space would be nearly indistinguishable from absence. Yet even in this extreme stillness, the laws of physics would not be broken. They would simply have reached a kind of conclusion. Gravity would no longer sculpt large structures because there would be no dense clumps left to pull together. Electromagnetism would persist, but with particles so far apart that interactions would be rare beyond imagination. The strong and weak nuclear forces would remain encoded in the fabric of matter, but with little matter left to bind or transform, they would sit quietly in potential. It is tempting to see this as an ultimate ending, a final page where the story closes and nothing follows. But cosmology has a way of softening absolutes. Some theoretical models suggest that even in a universe approaching heat death, quantum fluctuations can never be entirely erased. At the smallest scales, the vacuum is not empty. It hums with possibility. Particles can briefly appear and disappear, borrowing energy from the uncertainty allowed by quantum mechanics. In our current era, these fluctuations are subtle, overwhelmed by the grand structures of galaxies and stars. In the far future, they would remain, perhaps the only flickers of activity left. Over timescales even greater than 10 to the power of 100 years, extraordinarily rare fluctuations could, in principle, assemble small pockets of order. The probability would be almost unimaginably tiny, but given infinite time, even unlikely events can occur. A random arrangement of particles forming briefly into something structured, then dissolving again. Some physicists have speculated about so-called Boltzmann brains, fleeting self-aware configurations arising from pure chance in a high-entropy universe. Whether such ideas reflect reality or merely the mathematical consequences of thermodynamics remains uncertain, but they remind us that even in apparent stillness, the rules of physics do not switch off. They persist. And beyond that, there are models that do not accept heat death as the final state. Certain cosmological proposals imagine that dark energy itself may evolve. If its properties change, the expansion of the universe could slow, halt, or even reverse. In such a scenario, the vast empty cosmos would begin to contract. Galaxies, or what remains of them, would draw closer. Radiation would blue shift as space shrinks. Temperature would rise. The universe could head toward a big crunch, collapsing back into an ultra-dense state reminiscent of the singularity at the beginning. In that compression, space and time would curve more and more sharply. Density would climb, and perhaps, just perhaps, a new expansion would follow. A new Big Bang emerging not from nothing, but from the ashes of a previous cosmos. Other theories propose a bounce instead of a crunch. Instead of reaching infinite density, quantum gravitational effects might prevent total collapse, causing the universe to rebound before a true singularity forms. In these cyclic models, expansion and contraction follow one another endlessly. Each universe gives birth to the next. The quiet future beyond the last star would then not be a permanent silence, but a pause in a rhythm too vast for us to fully grasp. As you imagine this distant horizon, let your thoughts move gently between these possibilities. A universe fading into equilibrium, thin and cold, or a universe preparing for renewal through collapse. Both visions share something profound. They treat the end not as annihilation, but as transformation. Whether through infinite expansion or eventual rebound, the cosmos does not rage at its limits. It evolves toward them. The last star flickers out not in despair, but in completion. The last black hole evaporates not in violence, but in release. And the fabric of space continues, either stretching into calm or folding inward toward another beginning. In that perspective, the quiet future is less a void and more a threshold. If we continue forward in imagination, beyond even the evaporation of the last black hole, we arrive at a picture so minimal that it almost resists description. Space will still exist, but stretched to proportions that make today's vast cosmic distances feel intimate by comparison. The observable universe we now measure at roughly 93 billion light-years across will have expanded beyond any meaningful scale. Regions once connected by light will be causally isolated forever. Even the faint afterglow of the early universe, the cosmic microwave background, will have been stretched into wavelengths larger than galaxies once were. In practical terms, it will be undetectable. The universe will not go dark in a dramatic sense. It will become dilute. Entropy, that quiet accountant of disorder, will have reached a near maximum. Every process that could transfer energy from a hot region to a cold one will have long since completed. No star can shine without a temperature difference between its core and its surface. No wind can blow without pressure differences. No life can metabolize without gradients to exploit. In the far future, gradients vanish. The universe becomes uniform, not because it is destroyed, but because it has settled. This settling is not chaos. It is equilibrium, a state where change is no longer driven by imbalance. If we describe it mathematically, we would say that free energy approaches zero. There is still energy, but none of it is organized in a way that can perform work. Imagine a calm ocean at perfect stillness. No waves, no currents, just a flat surface extending endlessly. That is the thermodynamic fate predicted by the simplest interpretation of cosmic expansion with a constant dark energy. And yet, even here, subtle questions linger. Does time still flow in a meaningful sense when nothing changes? Our everyday understanding of time is tied to events. We measure it by motion, by oscillations, by transformations. In a universe where transformations are effectively absent, time may lose its practical identity. There will still be a parameter in the equations marking progression, but with no clocks left to tick and no observers to mark intervals, duration becomes abstract. The cosmos would exist, but not in the dynamic way we are accustomed to imagining existence. Some theoretical frameworks suggest that dark energy may not remain constant forever. If it were to intensify over time, expansion could accelerate to an extreme outcome sometimes called the Big Rip. In that scenario, galaxies would be torn apart, then solar systems, then planets, and eventually even atoms, as the expansion rate overwhelms every binding force. Space itself would stretch faster and faster until structure at every scale is pulled apart. This too would end in a kind of uniformity, but reach through disassembly rather than quiet fading. Whether this is physically plausible remains uncertain, yet it illustrates that the future may hinge on properties of dark energy we do not yet fully understand. There are also models rooted in quantum gravity that imagine a different destiny. In some loop quantum cosmology scenarios, the universe does not truly allow infinite expansion or infinite collapse. Instead, extreme conditions trigger a bounce. If contraction were ever to occur, the density and curvature of spacetime would increase until quantum effects counteract gravity, preventing a singularity in the classical sense. The result would be a rebound into a new expansion phase. In such a view, singularities are not terminal points but transitional bridges between cosmic epochs. Another speculative idea suggests that each black hole could give rise to a new region of spacetime, effectively seeding a separate universe. From within our perspective, a black hole appears as an endpoint, a place where matter disappears behind an event horizon. But from a deeper theoretical angle, the collapse inside might form a new expanding region disconnected from ours. If that were the case, then the death of massive stars in our cosmos could be quietly generating entirely new universes elsewhere, each with its own physical constants, its own timeline, its own stars yet to ignite. Our universe itself could be the interior of such a process, born from a collapse in a parent cosmos. If this sounds like science fiction, remember that these ideas arise from attempts to reconcile general relativity with quantum mechanics. The equations themselves do not forbid such possibilities outright. They leave open doors at the edges of extreme curvature. We simply lack the empirical access to step through those doors. So as we imagine the quiet future beyond the last star, we are left holding multiple potential endings at once. A slow fade into thermodynamic equilibrium, a tearing apart under runaway expansion, a contraction into a bounce, or a branching into new universes through gravitational collapse. Each scenario reframes the concept of finality. The universe may not conclude with a decisive period. It may transform, shift phase, or transition into something unrecognizable. What we call the end could be a local description from within one epoch of a much larger process. The singularity, whether at the beginning or at a hypothetical collapse, becomes less a wall and more a doorway whose interior we cannot yet illuminate. As your breathing steadies and your thoughts soften, imagine that distant horizon not as emptiness, but as possibility compressed beyond sight. The last star fading is not a tragedy. It is the completion of a chapter written in nuclear fire. The last black hole evaporating is not an erasure. It is the release of stored curvature back into radiation. And whatever lies beyond heat death or cosmic rebound is not silence imposed, but transformation unfolding at scales too large for our present senses to grasp. There is something deeply calming about imagining the universe so far ahead that every familiar landmark has dissolved. No constellations, no glowing spiral arms, no bright cores of galaxies humming with activity. The sky, if such a word still applies, would no longer be a tapestry of light but an almost featureless expanse. And yet, even this stark simplicity is not emptiness in the absolute sense. It is fullness redistributed, energy stretched thin across unimaginable distances, curvature flattened into near uniformity. The drama of gravity that once sculpted clusters and filaments would have completed its work. The restless thermodynamic dance that powered stars and forged heavy elements would have wound down. What remains is not destruction, but conclusion. If we look backward from that distant calm to our present moment, we see that everything now vibrant and structured is temporary. The atoms in your body were forged in stellar cores that will not shine forever. The galaxies we map with telescopes are transient patterns in an expanding sea. Even the laws we describe with equations may reveal deeper layers when pushed to extremes. The quiet future beyond the last star is not separate from us. It is the long trajectory of the same physical principles unfolding. In this immense timeline, our era is astonishingly early. We live in what astronomers sometimes call the stelliferous era, a brief chapter in which stars actively form and illuminate the cosmos. Compared to the trillions upon trillions of years that follow, this age is a bright spark at the beginning of a much longer night. The heavy elements that allow planets and chemistry and life exist because previous generations of stars collapsed and exploded. In time, that recycling will cease. The raw materials for new complexity will no longer be refreshed. The universe will transition from creativity through fusion to conservation through cooling. Yet some theories suggest that conservation is not the final word. In certain quantum cosmological frameworks, spacetime itself may not be infinitely smooth at the smallest scales. Instead, it could be granular, composed of discrete units woven together in a network more fundamental than geometry as we perceive it. If so, the extreme low energy state of a heat-death universe might not be perfectly static. Tiny fluctuations could still ripple through the underlying structure. Over unimaginable durations, these ripples might occasionally concentrate enough energy to nucleate new regions of expansion, small inflating pockets that detach from the parent vacuum. From within such a pocket, observers would perceive a new Big Bang. To them, their universe would appear to begin from a hot, dense origin, unaware that it emerged from the quiet vacuum of a predecessor. There are also ideas rooted in inflationary cosmology suggesting that our observable universe may be just one bubble in a much larger multiverse. In eternal inflation scenarios, space continues inflating in some regions even as it cools in others. New bubble universes can form continuously, each with potentially different physical parameters. If this picture is correct, then even as our own cosmic region drifts toward heat death, other regions could be igniting with fresh expansion. The quiet future of our universe would not imply silence everywhere, only locally. Creation and ending would coexist on scales beyond our horizon. Even the concept of entropy may take on new meaning in such contexts. Entropy increases within a given closed system, but if spacetime can branch or spawn new domains, then what we label as maximum entropy may be relative rather than absolute. A heat-death state might be stable within one cosmic region while serving as a backdrop for fluctuations that initiate something entirely different. From a philosophical perspective, this reshapes the notion of finality. The image of the universe fading into uniform radiation can feel austere, but it is not violent. It does not imply loss in the emotional sense. It describes a redistribution of energy according to consistent laws. The atoms that once formed stars and planets are not annihilated in a dramatic blaze. They are diluted, transformed, or radiated away. Structure dissolves, but nothing supernatural intrudes. The cosmos follows its equations to their asymptotic limit. If singularities exist at the cores of black holes or at the origin of expansion, they may represent boundaries of our current theoretical framework rather than literal infinities. A complete theory of quantum gravity might replace the notion of infinite density with a finite but extreme state, governed by rules we have yet to uncover. In that case, the beginning and possible ending of the universe would be transitions between phases of a deeper underlying reality. As you let this perspective settle, notice how the fear of an ending softens. The last star does not scream into darkness. It cools. The last black hole does not shatter space-time. It evaporates. The universe does not collapse in anger. It relaxes into equilibrium or shifts into another mode. What appears from within one epoch as the edge of everything may from a broader vantage point be a threshold. And perhaps that is why the concept of the singularity continues to draw us. It is both a limit and an invitation. It marks where our current descriptions fail and where new understanding might begin. In the quiet future beyond the last star, we confront not only the destiny of matter and energy, but the humility of knowledge. The cosmos stretches far beyond the timescales of civilizations. It evolves patiently, indifferent to urgency, yet entirely consistent. To imagine its farthest horizon is not to stare into despair, but to glimpse the serenity of completion. Now let your thoughts move to the very edge of this long unfolding. Imagine that the last star has cooled, the final ember of fusion extinguished trillions upon trillions of years ago. The final black hole, after a lifespan stretching toward 10 to the power of 100 years, has radiated away in a faint burst of energy and vanished. No more gravitational giants remain. No more dense knots of curvature anchor the fabric of space-time. What is left is a universe so thinly spread that structure, as we know it, no longer arises. Radiation drifts. Elementary particles persist in extreme isolation. Space continues to expand, carrying everything farther apart. This is the state we call heat death, though the phrase can feel harsher than the reality it describes. It is not an explosion, not a rupture, not a catastrophe. It is the settling of differences. Early in cosmic history, energy gradients powered complexity. Hot cores and cool surfaces drove stellar light. Dense regions and sparse voids shaped galaxies. In the far future, those contrasts are gone. Without contrast, there is no flow. Without flow, no new structure forms. The universe becomes uniform not because it is destroyed, but because it has exhausted the imbalances that once fueled transformation. If you try to imagine standing within such a cosmos, you might picture darkness. But even darkness is a relative term. There would still be photons, though so stretched by expansion that their wavelengths exceed any familiar scale. There would still be quantum fields permeating space, quietly fluctuating at the smallest levels allowed by uncertainty. Nothing dramatic, nothing bright, just an almost imperceptible background presence. A cosmos reduced to its most minimal expression. And yet, this minimal state invites a profound question. Is equilibrium truly the end of the story, or merely the limit of one chapter? Some cosmological models allow for the possibility that even in a high-entropy universe, fluctuations can occur. Given infinite time, rare configurations may arise by chance. The probability of assembling something complex from random motion is extraordinarily small, but when time itself becomes effectively unbounded, even the unlikely cannot be dismissed entirely. From the perspective of thermodynamics, these events would be statistical anomalies. From the perspective of existence, they could be seeds. Other models shift attention to the role of dark energy. If dark energy remains constant, expansion continues indefinitely, and the heat-death scenario prevails. But if its nature changes, if its equation of state evolves, then the ultimate trajectory of spacetime could shift. A slow contraction might begin. Distances that once grew could shrink. Radiation would compress and blue shift. Density would increase. In such a contraction, spacetime curvature would intensify until classical equations once again approach a singular limit. Whether that limit represents a true infinity or a transition governed by quantum gravity is unknown. But if contraction leads to a bounce rather than a terminal singularity, then the quiet end becomes the prelude to another beginning. There are also speculative ideas that treat singularities not as failures of physics, but as passages. In some theoretical extensions of general relativity, the interior of a black hole could be mathematically connected to a new expanding region of spacetime. If such processes are physically realized, then the death of stars in our universe may continuously generate new cosmic domains beyond our horizon. Each black hole would be less a tomb and more a cradle. In that picture, our own universe could be the interior outcome of a collapse in a larger parent reality. The Big Bang would not be creation from nothing, but emergence from a prior structure we cannot observe. If singularities are thresholds, then the end of our cosmos might not be annihilation but transition. The heat death we describe could represent the exhaustion of one mode of existence before a reconfiguration at scales too fundamental for our current theories to describe. The apparent stillness beyond the last star might conceal dynamics at a deeper level of spacetime geometry. What appears empty could be pregnant with potential. As your breathing slows and your mind drifts gently through these vast spans of time, hold this idea softly. What appears to be an ending may be a beginning compressed beyond sight. The singularity, whether at the heart of a black hole or at the origin of expansion, is both boundary and possibility. It marks where our equations falter, but also where new understanding may emerge. The universe may not end with destruction, but with transformation so subtle and so immense that it feels like silence. And perhaps that is why we return to this horizon again and again in thought, not to confront doom, but to encounter scale. to sense that our brief moment exists within a narrative stretching trillions of years into the future and perhaps infinitely beyond. The last star will fade. The last black hole will evaporate. Entropy will smooth away structure. Yet the laws that shaped everything remain. And within those laws, the potential for renewal may still be written. If you are still listening at this quiet horizon, type 3 in the comments.